لا بس swipe up red button that one تمام video good.
Hello everyone, this is our Capstone project, ROBOSOL, a robotic solar panel cleaner, second version of this project. These are my group members, Hussein Erin, Kunsuli Erdem, Murve Ganehan, Mohammad Buzariani, and myself, Abbas Fakir. This is the outline of our presentation. We're going to give you an introduction of the project, followed by the design objectives and constraints. We're going to then show you the configurations of our project, followed by the system breakdown structure, the engineering analysis and design, the manufacturing, operation and testing, and then we'll spend a bit of time on the cost analysis and the standards, then finish off with the contribution and future, and then conclude. So, the main objective of our project was to create a semi-autonomous robotic solar panel cleaner. As we all know, solar panels usually lose efficiency because of dust and dirt accumulation. And traditional methods of cleaning solar panels are very labor intensive or dependent on water, and they take a lot of time. So our goal was to develop a semi-autonomous robotic solar panel cleaner that will efficiently and sustainably clean solar panels. This is the organization of our report. We have 7 chapters followed by the appendix. Chapter 1 is introduction, chapter 2 is literature review, and as follows.
Primary idea of this design was to enhance the performance of the previous robotic solar panel cleaner by creating a more advanced ultimate application and optimizing the device's effectiveness and functionality by reducing its weight and size. In terms of the design objectives, we have design for cost, which was one of our primary goals, aiming to reduce the overall production cost of the solar panel cleaner robots. Then we have design for sustainability, which was also a crucial factor, involving the use of eco-friendly, easily recyclable materials and according to the United Nations sustainability goals. As for design for performance and effectiveness, we introduced synchronized wheels and an improved power supply, which are the vital elements in optimizing the robot's overall operational efficiency and effectiveness. Apart from these types of objectives, we also have design for manufacturing, design for assembly, design for maintenance, and design for safety.
These are our design constraints. Designing a solar panel cleaning robot involves addressing several critical constraints to ensure effective, safe, and economical operation. As it can be seen in this slide, we have financial limitations, which aims cost effectiveness while maintaining high performance standards with a target budget of less than $1,100. Time was another design constraint in this project, as we needed to complete the design and manufacturing without exceeding the due date, which we accomplished successfully. Also, availability was one of the main design constraints, as we couldn't find most of the desired components in Cyprus, so we ordered them from Turkey, which extended the delivery time. The other constraints are supply chain challenges and customs regulations, autonomous functionality, environmental factors, manufacturing limitations, sustainability, and manufacturing.
So we did a lot of literature review for this project, especially because there's a previous version of this project, and we realized that existing robotic solutions have cleaners that are mounted on the solar panel. So they're built customly for that solar panel. Our goal was to make a robust design which would, you could just place it on any solar panel and it would just clean the panel. Another cleaning method we found was self-cleaning solar panels. These work by putting a coating on the surface of the solar panel, and with the help of electric charge or hydrophilic coating, it repels dust. But this was found to be very less effective, especially in humid or rainy environments, and over time it would degrade a lot. These were our design configurations last semester. We chose this design to be our main system, and we replaced the track wheels with mechanism wheels for more advanced mobility. Then this semester we decided to make it more simple for manufacturing. We made the chassis simpler for manufacturing and made the brush case simpler so we could 3D print it in one go. We used the mechanism wheels for enhanced mobility and a LiDAR sensor on top. There's a Raspberry Pi camera for image processing.
first start with calculating the power needed for each stepper motor to work. So first we start with calculating the force needed per each wheel to make the robot move uphill against the gravity, as you can see here. The force needed per each wheel is 70.34 Newton. And we calculated the torque using this force. We got 0.6936 Newton per meter, and we also calculated the angular speed as we need it in our equation for the power. And we got at the end 12.4 watts per each stepper motor. For the capacity of our battery, we first calculated the total power consumption needed in our operation. Then we got the capacity in watt per hour. Then we transformed it to milliampere hour. We got 12,780 milliampere hour. And in the market, we found this lithium battery with 13,000 milliampere hour, which has a discharging duration of 1 hour 42 minutes. And then we calculated the power needed by the plant. As we can see here, we assumed a flow rate of 2 liters per minute, and the atmosphere as 1 bar, which is 10 to the power 5 Pascal. We got 3.3 watts. Then using a 0.5 efficiency, we got the power of the motor, which is 6.77 watts. And here we have mass budget table. We calculated the mass, predicted mass of our robot. We got 5.5 kilogram. And here we have a table represent the required current in our circuit, which is the total is 7.66.
Throughout the manufacturing process of our robots, our aim was to use economical and less complex machining to keep up with the 12th goal of the United Nations Sustainable Goals, which is responsible consumption and production. We tried to use eco-friendly manufacturing processes. We started with the CNC machining of the aluminum chassis. We used aluminum due to its malleability and durability. For the chassis, we recycled an aluminum piece with a thickness of 6 millimeters that was originally a piece of higher precision engineering project by cutting it to our design dimensions using CNC milling machine and by removing the minor imperfections on its surface. For the main body parts, as you can see here, the main body parts and the brush cover, we use PLA with SDM 3D printing as it's a biodegradable material suitable for recycling. Then we painted the 3D printed body parts with a spray paint suitable for thermoplastics. Also, we ordered the cylindrical brush to be manufactured by a company in Turkey according to our design dimensions and specifications, involving the enhanced and smoother bristle material to reduce the risk of the solar panels from getting damaged. Finally, in order to combine the brush with its cover and its DC motor, we 3D printed the key bushings to place on the end of the brush.
To assemble the manufactured parts together, my teammates described, we used the drilling machine in our workshop to drill the chassis and the main body parts, and used metric force screws and nuts with L brackets to combine them together to create the robot's body. Then we used the same screws to attach the stepper motor of the wheels to the main body. We also increased the diameter of the couplings of the wheels by 1 millimeter on the lathe machine, as they were not fitting to the shaft of the stepper motors. Apart from the screws that we used to combine the cover and the front body part, we use strong glue to secure the cover in its place to be sure that it doesn't move while the DC motor attached to the cover is turning with the brush.
The DC motor we use to turn the brush is a 12-volt, 5,000 RPM DC motor with a gearbox attached to it to reduce its speed to 90 RPM. The gearbox on the DC motor converts the high speed
Can we check?
It's called scissor mechanism. Scissor mechanism.
As in the first two videos, we tested the DC motor of the brush and validated its effectiveness in turning the brush off the robot. Then we tested the NEMA 17 stepper motors one by one to check their ability to turn to both sides with different speed inputs, and we saw their capability to work smoothly and to follow the given commands.
Here you can see the cable manage what we did for the RB1825 motor drivers and second motors. And here we tested the ultrasonic sensor for autonomous control.
So after we finished the robot, we tested the dimensions of it. The overall length of the robot was 41 centimeters with the brush. The wheel diameter was 8 centimeters, and the total width of the robot was 37 centimeters. We used special brushes, as they mentioned before, with soft nylon material that was custom made to clean solar panels from a company in Turkey. We're going to show a demonstration video of our robot now. The robot works at a maximum angle of 15 degrees in this video. We decreased the speed of the robot so it would clean the surface more efficiently. Yeah. Once it detects the edge, it stops it. We tested the robot with a small pump and detachable water tank. It wets the brush through these holes in the pipe, and the wet brush then cleans the surface.
Why did you stop?
Yeah, for you, man. But the sensor doesn't work.
Before,
Why do you hold it like safety?
for here we have FMEA, failure mode. We use this FMEA to identify some potential failure modes, and we found out that the most crucial one is for Raspberry Pi, as we got in our RPN 128. And we use also fault tree analysis to identify any problem in our systems. We divide our system into 4 systems, as we can see see brush system, electrical system, motor system, and dry system.
At the moment you guys have been waiting for the comparison with the previous project. So our main goal was to make it lighter and more compact. We decreased the weight by almost half, as you can see. We also reduced the size by almost half, as you can see. Their brush was also bigger because it was handmade and it had a thick shaft. We got it custom made from Turkey, so our brush was also half in size. The battery they used was a lead acid battery with 4,500 milliamp hour. Ours was a lithium iron phosphate battery with 13,000 milliamp hour. It was also a third of the weight.
Here in the right, you can see the cost of each component we bought. The most expensive one was the battery. It was 3,600 Turkish lira. The cost of the components is 20,321 Turkish lira. Our total cost was 21,895 Turkish lira. The estimated cost I was looking before was around 47,000 Turkish lira. We tried to find the cheapest but high quality components for our project, which made it way more cheaper than our estimated cost.
We tried to understand the engineering standards you see on this page, and we tried to apply them in various stages of our project, like design, production, assembly, testing, and safety also. We also needed some specific standards for the equipment we use in the robot, one of which is the mechanical wheels. ISO 19649 standard regarding mechanical wheels, it defines a mechanical or omnidirectional as a wheel equipped with rollers on its outer surface, facilitating movement in any direction, even perpendicular to the wheel itself.
This was the Gantt chart of the project. This was the first half, and this was the second half of the project. We tried to follow these three specifically UN Sustainable Development Goals. Goal 7 about affordable and sustainable energy, Goal 9 about innovation, and Goal 12 sustainable consumption and production. The future works of this project, we would like to include another brush at the rear end of the robot, so it could deal with the excess water as you saw in the video. The other thing we would like to do is use ASA filament instead of PLA filament, because it's better. But we could use it because it requires a closed 3D printer, which we couldn't find inside.
Also, we are planning as future work to use LiDAR sensor for mapping the environment of the robot automatically with integration of robotic operation system that will make like an environment which have a master and a lot of nodes for each electric part. And also we will integrate the AI by using A-star search algorithm if we can make an admissible heuristic for this algorithm. Also for predictive maintenance, we are going to use ROS as it will give us
To conclude, we can say that our solar panel cleaning robot fulfills the pivotal design objectives through its autonomous working principle with the help of ultrasonic sensors. Its compact size and lighter weight compared to the previous version. Its enhanced mobility using the mechanical wheels to navigate easily on the solar panels, and its robust design ensuring the durability and reliability. Additionally, the use of biodegradable PLA for 3D printing aligns with the United Nations sustainability goals, showing our commitment to eco-friendly practices. By addressing the critical need for maintaining solar panel efficiency, our innovation promises to maximize energy output and contribute to a greener future. As our last verse, I believe that we tried to do our best for this project, and finally we came here with this robot. We always dreamed something better, but we experienced very big complications from time to time. We lived a few minutes ago. I'm sure these problems taught each of us many different things, but despite everything, we didn't refrain from putting forward an idea, a philosophy, and I believe that this aspect of ours will push us to do more successful works and projects in the future. We mentioned it in our report, but I want to thank once again everyone who supports and believes us. Also, on behalf of myself and my teammates, I want to thank you, to each of you, everything you have given us and for your time. Thank you.